just draw a sort of technology, if you like. Well, I'm going to call it the artificial leaf. So you have something like this. You have a membrane here. This is going to be some sort of membrane. And on this surface, you put a catalyst. And semiconductor, when a semiconductor absorbs light, many types of semiconductors, it absorbs, light comes into it. This would be light. And it causes a charge separation, like that, in the semiconductor, between the so-called valency band and the conduction band. And so here you have a high energy electron, just as you do in photosynthesis, which can be used by some catalyst to carry out a reaction. Now that reaction could be this one, where it takes a proton, like that. It supplies an electron and you make hydrogen. Or it may be a catalyst. Let's do another one down here. And this may be CO2, and then you may make, for example, CH3OH. On this side you have the hole, and you want to have a catalyst, it'll be the same catalyst now, that will take water, and you take the electrons out of water to neutralize the positive and release oxygen. And of course it releases protons as well. Now those protons, you see we wanted protons there, and we got protons here, called H plus a proton. So we have to have a system by which you may have a mechanism by which you can take this proton, that's for the moment, has to go round here, as you have to go round to there. So you've got protons and electrons, and they have to combine to make hydrogen, or you also need the proton. You also need a proton here, because you're going to make methanol. You need hydrogen there as well. This is an extremely bad diagram. I can show you much better on my slides, but maybe I should draw it again. What do you think? So the idea then, light is absorbed, you form a positive charge and a negative charge. So that's the storage of energy. You use the negative charge, the electron, to reduce protons, or convert protons into hydrogen. Or alternatively, you use the electrons to reduce carbon dioxide, it's not very clear, it's terrible, into a fuel like methanol. But it's not easy to do because these are hard reactions. They're not single electron reactions, they're 4 electron reactions. So you can't do this reaction with one positive, you have to have 4 positives. And on this side, similarly, if you want to make ethanol, you have to have 6 negatives. So it's not a simple one electron process. So these catalysts that you have here and here must have the ability to accumulate 4 pluses, not 1 but 4. So the catalyst must be able to accumulate, be able to cope with 4 protons. So you've got to form 4 positive charges. So the example I've given you is cobalt 2 plus linked to another cobalt 2 plus. For example, it's only an example. With 4 photons, we'll give it cobalt 4 plus, cobalt 4 plus. Now, in the natural enzyme, so there are people working on cobalt catalysts. In the natural photosynthetic water splitting enzyme, photosystem 2, which I've worked on, the catalyst is actually made of manganese. So you have manganese, you have 4 manganese, manganese 3 plus, linked to another manganese 3 plus, 3 plus. So here's a starting point. Then 1 photon comes along, 1 photon, and you get manganese 4 plus, manganese 3 plus, manganese 3 plus, manganese 3 plus, right? And then another photon, and then another photon. So we go again, and you end up with one of these are 4 plus. I don't want to draw it all out again. And then you go again. So we're already down here to manganese 4 plus, manganese 4 plus, manganese 4 plus, plus manganese 3 plus. So now the final step, the final photon, gives you manganese 4 plus, manganese 4 plus. Now you've accumulated, there was, how many pluses there? There was 12 pluses there, now there's 16 pluses. So you've accumulated 4 pluses, 4 oxidizing equivalents, we would say. And at that stage, the 2 water molecules are, in chemical terms we say, oxidized, and an oxygen molecule is released. So it goes back to our equation here, that 1 oxygen needed. So you've taken up, 4 electrons have been taken out of this manganese cluster, and 2 water molecules and 4 protons are released. Not quite like that. Protons are released to go around, and obviously I've left that one out there. So this is a catalytic cycle, which is not a 1 electron, but 4 electrons. So in making a catalyst to do this reaction, e.g. one that's, say, composed of cobalt, you need to accumulate positive charges. That's what makes it quite difficult. But from the catalytic point of view. But nevertheless, there are very interesting catalysts, and some that we're working on here in Italy, in Torino, which are cobalt-based, and also manganese-based. We're also looking at manganese systems. But in the end of the day, the catalyst has to be cheap. You know, it cannot be expensive, because we want to do this on a massive scale. So we have to look for cheap materials. You can do these reactions often with very expensive materials, but here we must have cheap materials. So, and also on the other side of this device, the device, I'm going to draw it much bigger now. The device. Okay, we've been talking about the catalyst here that's going to make oxygen. It's going to make protons, 4 protons, and it's going to split 2 water molecules to do that. And and now that's done, driven by this charge separation, which is being separated by light. But we have to do it 4 times, and that's what happens in natural photosynthesis. You have to give 4 flashes of light in order to get the reaction to work. Now on this side, it can be very complicated. So if we want to use this electron to convert carbon dioxide, for example, which would be good, into methanol, OH, we need to have 6 electrons to do this. So this means even the catalyst has to be even more complicated than the one I've been talking about. So this is the challenge, is to develop these catalysts to deal with what we call multi-electron chemistry. Of course, this is a very attractive thing to do, because in principle you can recycle CO2. So CO2 might be generated initially from fossil fuel, coming from a power station, and it normally will go into the atmosphere. But if you develop the chemistry, you can convert it back into fuel and use it again, and use it again. And if we were very, very clever, we would do what the leaf does, because in photosynthesis, the CO2 in the atmosphere, which is at very low concentrations, the concentration of CO2 in the atmosphere is about 0.04%. It's very low. And so it's hard to do chemistry when you have a very low concentration of the reactant. So again, if you could develop a mechanism to concentrate the CO2, to do the catalysis, the chemistry, that would also be very interesting. So in Torino, we're interested in something called MOFs. And these are metal oxygen frameworks. These are molecules which have cages which absorb gases. They can absorb CO2. And so by using a MOF with a metal oxide framework, with a catalyst in it, you've increased the concentration of your CO2, and that would much higher than the atmospheric level. So it's going to be difficult, but it may be possible to develop systems that can absorb CO2 out of the atmosphere. But as you can see, it's quite hard to do that. Of course, it's easier to use CO2 when it's enriched, when it comes out of a power station, for example. But of course, so much of the CO2 comes from out of the backs of cars and so on and so forth. So if we could develop systems that can concentrate the CO2 and then carry out catalysis to make a fuel, then we get into a cyclic system. That was the whole point of this, is that it's a cyclic system. You make CO2, but you convert it back again to a fuel. You just go, or you make hydrogen, but you burn it back to water, so that you just keep in a cycle which is in balance. Then if we can learn to do that, then on a very large scale, then we've solved the energy problem, and without any pollution of the planet. But the problem is, at the moment, we don't have this technology, and of course the CO2 level continues to rise in the atmosphere. And at the moment, I don't think we know really what to do with it, to be honest with you, how we're going to solve this problem of CO2 emission. Of course, the governments have very strong policies at the moment to try to reduce CO2 levels going into the atmosphere, but really we have to be much cleverer, and we've got to develop this artificial photosynthesis, and it has to be done on a very large scale.